Yeah, that's great. Okay, so this is our last talk. I guess there's echo because of the microphone. So it's scaling up Livelock verification for network-on-chip routing algorithms. Please go ahead.
All right, so well, good morning. My name is Landon Taylor, and I'm an undergraduate researcher mentored by Zheng at Utah State University. And we're presenting our work on scaling up Livelock verification for network-on-chip routing algorithms. So network-on-chip is an on-chip interconnection network that governs on-chip communication between homogeneous routers for many core systems. And it gives us a solution to increase design complexity, especially as systems advance and develop. And it lets us balance processing loads among many cores. And it's an elegant improvement on static bus architectures that are traditionally used. So our work provides three main contributions. We present a refutation-based verification approach that lets us scale our verification from a 2x2 network to a 15x15 network. We then use a zone-based abstraction method to verify correctness on an arbitrarily large network. And our main contribution is a Livelock-free fault-tolerant routing algorithm, along with a proof of that algorithm's correctness. So our work relies on two main verification tools. We rely heavily on the IV tool for inductive invariant checking, and that's developed by Ken McMillan and Oded Pedun. We also use property-directed reachability as implemented in the ABC model checker. So network-on-chip, or the network-on-chip system we analyze is a 2D mesh network with a coordinate system, as shown here. And in hardware, these nodes use routers and arbiters to forward and receive packets, as well as generate and absorb those packets. In our work, we abstracted all of that away and treated every node as a single unit that can send and receive packets just as one unit. So this network must be able to provide provable safety guarantees or correctness guarantees, especially if it's used in a safety-critical system, such as a self-driving car or rocket ship. And tolerating faulty connections is very desirable. So if one of these faults between nodes, or one of these links between nodes becomes faulty, we want to be able to forward a packet around that fault. However, tolerating those faults can introduce flaws that other testing and verification methods might miss. And one of these flaws is Livelock, which causes a packet to cycle forever while using up power and worsening the traffic in the network. So the routing algorithm we analyze is a fault-tolerant routing algorithm. It was originally presented in our earlier work. And it forwards west, or overshoots west first and then south. So for example, a packet starting in S1, in order to reach node D1, will first travel west before going south to its destination. And this, as shown in a packet starting in S2, allows it to avoid this link, or navigate around this link fault, and tolerate faults in this arrangement as well. A packet starting in S4 shows an overshoot to the south. So this packet travels south one node first, then east toward its destination. Interestingly, this algorithm also lets us tolerate two faults. So if we start in S7, for example, and we travel south first to overshoot the destination and run into a fault, we're able to route two nodes to the north and loop around to the destination. So while this is desirable to get packets to their destinations, this excessive fault tolerance can sometimes lead into Livelock scenarios. Okay, is that better now? All right, so just to define some terms, a trace records the history of nodes or coordinates that Oh, it's telling me the battery is dead. Sorry about that. There we go. Sorry about that. So defining some terms, trace is the history of nodes that a packet has visited. A livelock pattern is an infinite cyclical repetition of nodes in a trace. And this livelock must include cyclical behavior or a series of repeated changes in a packet's traveling direction. We define a livelock prefix to be a finite sequence of nodes that precedes a livelock pattern. A livelock trace is a livelock prefix immediately followed by a livelock pattern. So a livelock free trace is simply a trace that contains no livelock pattern. A livelock free network contains only livelock free traces. And packets that are delivered to their destinations or determined to be unroutable due to conditions in the routing algorithm are automatically not in livelock. So here's an example of what a livelock pattern might look like. So a packet would start in node 2.1, and rather than, or because there's a fault here, it can't be routed north to its destination. So it's routed west, but because of this fault and a nuance in the routing algorithm, it's routed south instead of north, and that starts it traveling in this infinite cycle. So to detect and remove these livelock scenarios, we started out using a refutation-based simulation approach. So we implemented the network in a C++ simulation, and we just exhaustively simulated every combination of starting and destination coordinates that a packet could have, as well as every combination of possible faulty links with up to 2 link faults in the network. And we ran these simulations with a bound of k steps. Since we were dealing with networks of only about 9 or 10 nodes in the network, we set k to 1,000. We figured if a packet takes 1,000 steps to reach its destination in a network with 9 nodes, something has probably gone wrong and that needs our attention. Once we've run that, we ignore all of the traces that terminate within k steps because those are proven not to contain livelock. And all of the traces of length k, we use them to automatically construct invariants that let us verify if that long trace is in fact a livelock pattern. So we use IV to verify a set of invariants. So when we ran the simulation, we got 2, on a 3x3 network, we got 2 novel livelock scenarios or scenarios that we had missed in our previous work. And that's this counterclockwise pattern directly below a destination and this clockwise pattern directly to the west of the destination. So this is the first invariant that we automatically construct. And it just indicates that a packet's destination must always be the same destination we used in the simulation to produce that livelock pattern. This second invariant indicates that if a node xy or a node xy that is not in the livelock pattern must not have a packet. So this new xy indicates the node has a packet. And we enumerate this for every node that is not in the livelock trace. Invariant 3 basically says that every time a packet leaves a node within its livelock pattern, it will be traveling in the direction that leads to the next node in the livelock pattern. So looking at this example, if a packet is in, if a packet is in this node, we know that it must have traveled west to get there. And that's indicated by this tau with the coordinates. Our fourth invariant is similar. It says that any packet within the livelock pattern, or in a node within the livelock pattern, must have been forwarded or must be forwarded to its immediate next node within the livelock pattern. So that says that if a packet is here, its previous node's coordinates must have been that of its predecessor node. So using those 4 invariants, we verify that all of our scenarios that were of length k were in fact Livelock scenarios. And we use this iterative process to remove Livelock from the network. So we prune the Livelock prefix and identify every turn in the Livelock pattern. We then go through and manually adjust the conditions for the routing algorithm to help us eliminate Livelock. And we decided to keep this process manual because when a user, or when it returns many different Livelock scenarios, a user can see, maybe there's an issue with every Livelock involving a left turn with a certain link configuration. So after we've made these modifications on each turn, we simulate the model and we implement the modification that gives us the fewest potential Livelock scenarios, or the fewest traces of length k. We then simulate the model and repeat the entire process until Livelock is removed. So we were able to remove these Livelock patterns on a 3x3 network and scale up to 15x15, producing effectively a Livelock-free routing algorithm for square networks scaling from 2x2 to 15x15. And we noticed as soon as we removed Livelock patterns on a 5x5 network, those patterns were somehow magically removed from every network larger than 5x5. So that led us to create a zone-based network abstraction where this black square represents the destination. So in IV, we encoded all of our conditions from the routing algorithm as predicates. So for example, if a condition in the routing algorithm requires a packet to be northeast of the destination, one of those predicates would be is northeast of the destination. We then use IV to check which nodes in a network contain or satisfy what set of routing conditions or these predicates. So we did this scaling up. So trivially, every node in a 1x1 network is unique, and every node in a 3x3 network ended up being unique as well. So we scaled up again to a 5x5 network with the destination fixed here in the middle. And IV let us know that these 4 nodes in the northeast corner could all be, or all satisfied an identical set of predicates. So because they satisfied the exact same conditions in the routing algorithm, any packet within these nodes would make an identical decision under the same link configurations. So we effectively merge those nodes into a routing zone. And we were able to do that with several nodes here. And these letters are chosen arbitrarily, and they don't mean anything translated from one network to the next. And we were able to continue scaling this up all the way to being arbitrarily large in size, producing these routing zones here. So this let us define in IV this zone-based routing algorithm. And we also included a concept of an abstract move. So the network is constructed on the fly. A packet moves non-deterministically, and essentially it can move any direction so long as the link is available in that direction. So if there's a faulty link, obviously it can't go through it. So in order to detect arbitrarily large cycles, we used an abstract move where if a packet travels any length without changing its traveling direction, it's considered to be one abstract move. As soon as it changes direction, that becomes a new move. So if a packet travels from this node marked E, for example, to the node marked B, that would be considered one move. And then if it was forwarded to the node marked L, it would be a second move, from E to B, then from B to L. So using this method also requires us to have several heuristics. This edge heuristic is just an example of one, and we'd encourage you to look at our paper for the rest. But the packet, essentially, if a packet travels all the way to an edge and then travels parallel to that edge, the network's edge should be maintained. We're not necessarily interested in a zigzag topology. So this heuristic basically says as long as you're traveling parallel to an edge, that edge must be maintained. We also had to have or sort of modify our definition of Livelock, where previously we were interested in an infinite length trace. We're now interested in more cyclical behavior and changes in traveling direction. So we define Livelock using several of these predicates. We just chose one for the slide for simplicity. And this can be read as tau indicating the traveling direction and its subscript indicating how many moves ago that happened. So this is saying 6 moves ago it was traveling south, 5 moves ago it was traveling west, and then it traveled north, east, south. And this represents a clockwise loop, essentially. And using several of these predicates together, we can guarantee none of this looping behavior occurs in the network. Something worth noting is we made this definition or this predicate of length 7. So to avoid false positive Livelock scenarios, we noticed that some packets, in order to avoid faults, would travel in a loop, but then be able to exit that loop and proceed to a destination. So to exclude that, we simply added turns to the Livelock definition predicate. To generate as many counterexamples as we could, we sort of trick Ivy into returning new counterexamples every time it runs. So we define this sigma 0 as these Livelock predicates. And we state that essentially either there is no Livelock matching that Livelock predicate, or the Livelock that we find matches one that we've already found. And that tricks Ivy into giving us novel examples every time we test the network. So here's an example of what that might look like in Ivy syntax. This P is a packet object, and sent6 is the same as tau6 or the traveling direction 6 steps ago. So this is essentially saying, there's none of this looping behavior, and in disjunction we add, if it is that looping behavior, then we hope it's this Livelock scenario that we've already found. So this is indicating that it's a Livelock pattern between zones I and J, and that it has this link configuration described here. And interestingly, that's this counterexample we found in our abstract model between zones I and J, which really shows the value of our zone-based abstraction. So this counterexample we obtained from our simulation shows this very similar pattern occurring directly below the destination. But with our zone-based abstraction, we see that this could actually have occurred right here below the destination, where R is the destination, or it could have occurred 10,000 nodes south of where it was. And we would have never found that with using a fixed network size. So the guarantee we can offer with this zone-based abstraction is actually stronger than a guarantee of Livelock freedom. We can guarantee that no packets ever exhibit cyclical behavior with a cycle of length 7 or greater. So in conclusion, we've had 3 main contributions in this work. We used the refutation-based verification approach to scale from a 2x2 to a 15x15 network. We used a zone-based abstraction to scale to an arbitrarily large network. And we present a Livelock-free fault-tolerant algorithm with proof. And we don't go into the details in the slides, but we'd encourage you to look in our paper for that algorithm. Continuing this work can include using the zone-based abstraction method to verify other properties of a network, such as deadlock freedom. as well as applying these methods to other network topologies and other routing algorithms. So thank you for your attention, and I'm happy to entertain any questions.
Thank you. All right, let's see if we have any questions from the live audience.
Let's see. I have a question, but I can wait.
Oh, there's no questions in Q&A.
Okay, so then
there is a question.
Yeah. So I was wondering. So the algorithm, how many link failures can it tolerate?
It tolerates, so there's no livelock and 100% packet delivery with 0 or 1 link fault. And it can deliver many packets with 2 link faults. There's some, for example, if a packet is trapped in a corner and can't escape, that it just won't be able to avoid those faults. But
yeah, so I'm kind of curious if you could sort of encode other topologies just by having sort of initial link failures, and then maybe by excluding some sort of corner cases like packages getting trapped, you could still use your technique.
Yeah, that would certainly be a way to encode another topology. Just adding, if I understood right, just adding link failures.
Yeah, exactly.
Throughout the network. Yeah.
Okay, thank you.
Okay, so there is a question from the Q&A. It's on the screen right now, at least on my screen. And it says, it's from Andrew Johnson, and it says, did you consider a routing algorithm with non-determinism to pick direction? That seems like it would solve most of the examples shown.
Let's see. So
we have to just reconfigure our setup for a second.
We do get audio from you, but we lost the video.
Oh. Let's see. Would you be able to repeat your question? I'm sorry.
So it's not my question. It's Andrew Johnson again.
Oh.
And the question is, did you consider routing with non-determinism? It looks like it would solve most of the examples shown.
We hadn't considered an algorithm with non-determinism. We actually were looking just at this one specific algorithm, but that would be a really interesting case study to pursue in the future.
Not sure how you would implement non-determinism, but maybe if you replace it with randomness, you can have a probabilistic guarantee.
Yeah, that would be very interesting to look at, for sure.
Okay. Do we have more questions?
I don't think we have any questions in the audience, live audience.
All right, well, I can ask a question. So as you were presenting, I kept waiting until symmetry will appear, because it seemed like the system is very symmetric. But it never appeared, and it looks like your zone abstraction is quite asymmetric. Can you say something about that?
Yeah, so because we overshoot west and south first, there's a sort of symmetry within the network. It's actually along the diagonal. Like if you were to plot x equals y, it's mirrored symmetry across that. We actually didn't think to implement anything using that symmetry, but that's an interesting observation for sure.
I see. So you're saying there is symmetry, and maybe there's something that can be done with that.
Yeah, it would definitely be interesting to investigate that.
I see. Okay, that's interesting. And another question I had is about the tools. So I'm building tools like this. I'm always interested in people who use them for interesting things. Can you comment about your experience with Ivy and ABC? Like what didn't work, what was hard, what was easy, or?
So our first approach actually completely failed. We, of course, didn't mention it in the talk, but one major issue we had with Ivy is that it would return a violation of an inductive invariant, which in a lot of cases is desirable, but in our case, it was giving us traces from completely unreachable scenarios. So we actually found that the property-directed reachability had been implemented in Ivy. So essentially, you could run the same Ivy model through property-directed reachability, excuse me, and it would actually give you a trace, a finite trace from start to end that was guaranteed to be a reachable trace. So that addition made Ivy probably my favorite tool I've used for verifying things.
And the modeling in it was convenient? Because you have to model things in a particular first-order style.
It was pretty simple to learn. It has very good documentation on their website. Yeah, it's really it's almost like writing C code to build these models. It's quite simple.
Okay, it's nice. All right, do I have any additional questions that I missed? I don't see anything on Q&A, Thomas?
Let me just double check. I think we have everything covered.
Okay, well, let's thank our